Okay, not a ton left to do. It starts to lighten up just a little bit here. But next to that, we got to talk about area and volume. I'm not actually going to review anything there. I just want to remind you guys that is fair game and it will show up on the test. So review your area and volume formulas and calculations. Next up is receptacle spacing. Again, I don't have too much to say. I do want to remind you really briefly, sort of, first of all, Article 210, particularly 210.52 is where you're going to find that information. In general, if we're talking about bedrooms, living rooms, general areas of the house, the code's going to read that no wall space can be more than 12 feet, or I'm sorry, start over. No wall space can be more than 6 feet from a receptacle. That is to say, my receptacles can be a maximum of 12 feet apart. Again, think of, I take that lamp with a 6-foot cord, I place it anywhere in the room. That cord needs to be able to reach a receptacle one way or another. Any wall space 2 foot or greater is going to require a receptacle again. If I apply the same logic, now let's talk about kitchen countertops. Same exact logic, same exact thinking, except that the distances shrink up. So now, no wall space can be more than 24 inches from a receptacle. That is to say, my receptacles can be 4 feet apart from one another maximum. Any wall space that is 1 foot or greater is going to require a receptacle. Burial depths, on to our next little section here. Burial depths, we reviewed this pretty hard in midterms. It seemed like most everybody did pretty good with this. But I do want to remind you that all comes from table 300.5. Don't forget it. Switches. There's a bunch of different miscellaneous stuff on switches. Nothing too in-depth, nothing too wild. But we should mention, we have essentially, I'll call it 4 different types of switches. I would maybe argue even 3. But you have your single pole, single throw, right? One in, one out, open or close, on or off. 2 terminals for connections of conductors. Then you have your single pole double throw. 1 in, 2 out. It's either this or either that. There is no true on or off. It's always connected to one or the other. We have a common screw, then we have our 2 traveler screws, 3 screws for connection of conductors. Next up, we have our double pole double throw. That would be 2 in, 2 out. That is, and I'm actually pointing to the wrong one, your double pole double throw, I should say. That's going to be either this or that. Once again, we never have a true off. In this case, we have 4 screws for connection of conductors. Then the last one is your double pole single throw. So we have, again, 2 in, 2 out. We have 4 screws for connection of conductors. But in this case, we do have that true on or off. On, off. This one we're going to refer to as a single pole. This one we're going to refer to commonly as a 3-way. This one we're going to refer to commonly as a 4-way. This one is referred to commonly as a double pole. We don't really talk about it as much. But switches, that was certainly not everything you need to know, but I think that's a really nice overview. Again, they don't get too far in depth. They really just strike the surface on the switches. Probably the biggest thing we have left, the biggest topic, is your voltage drop, right? So we really have 2 different formulas that you need to be aware of with voltage drop. The first being, I guess we first have to ask ourselves, what are we looking for when we talk about voltage drop? Are we looking for how many volts are we going to drop? Or are we looking for what size wire are we going to need to run? So there's 2 different ways they might ask a question. One, they want to know how many volts you drop. One, they want to know what size wire do I run. Depending on what you're looking for, depends on which formula you use. If you want to know how many volts you're going to drop, if the volts are the unknown, we're going to use this formula with the volts on the left side of the equal sign. If we want to know what size wire to run to maintain a certain voltage drop, so the wire size is unknown, we're going to use this formula where CMA is on the left of the equal sign. Again, CMA, circular mill area, another way to say wire size. Aside from those 2 formulas, we also need to know once more in Chapter 9, the back of the NEC, Chapter 9, Table 8 in this case. Chapter 9, Table 8 tells us a whole bunch of stuff, but for our purposes, most importantly, it tells us the circular mil area, the CMA, of any given wire. Right? Once again, at 250 kc mil, they stopped telling us. That's because kc mil stands for 1,000 circular mils. So 250 kc mil is 250,000 circular mils, right? So yeah, here's an example problem let's use. And let's just review quickly. VD is how many volts we drop. 2 is a multiplier we use for a single pole circuit. Were this a 3-pole circuit, we'd actually use the square root of 3, 1.732. For your purposes, in this year, it'll always be single pole circuit, so you're always going to use 2. I is going to be amperage, L is going to be length, and then K is basically the resistance of our conductor. I believe on the test, in all cases, they give you the K value. Generally, they're going to give you a K value of 12. I think for copper, it's technically 12.9. For aluminum, it's 22.1, something like that. But they always give you the K value in the problem here on the test. So, with that said, let's look at a example problem here. Let's say we're going to run some number 10 gauge wire. We're going to have a 25 amp load. We're going to run it 200 feet. We're going to use a K value of 12, meaning we have copper wire. So the question is, how many volts am I going to drop by doing that? Well, what I don't know is the VD, the volts drop. So I'm going to use this top formula here. So let's start filling it in. Again, we don't know VD, so that stays here. We're going to run a single pole circuit. Our amperage is going to be 25. And I'm actually going to type it like, well, no, I'm not. Our amperage is going to be 25. Our length is going to be 200. Our K value is going to be 12. Then on the bottom here, let's get a little underline action going. Then on the bottom here, we're going to divide by the CMA. So if I'm using a number 10, what's the CMA of a number 10? 10,380. Okay, so that's what my formula looks like. So we remember order of operations. I'm going to have to first solve for this top portion before I can worry about the bottom portion. So I'm going to go ahead and type that in here and let it solve for me. Okay, so that's 120,000. Well, that's a nice even round number, isn't it? Divided by this bottom portion now, 10,380. So I'm going to drop 11.5607 volts in that entire run. So then you might take it one step further and say, what is your voltage drop percentage, right? And, or you know, am I within 5% voltage drop, or however we want to look at that. But what we're going to do simply is 11.5607 divided by, and for this we have to know what is our starting voltage. Let's say it's 240 volts. It doesn't matter at this point, but let's say we're 240 volts. I'd take my volts drop that I just calculated, divided by the source voltage or the circuit voltage. I get 0.482. To put that into a sort of a percentage, I can multiply that by 100, or just move the decimal point 2 places. Either way, apparently that's not going to work, so we'll do this. That's 4.82. So I have 4.82% voltage drop on there, right? So yeah, that I think is your last really big topic on the voltage drop stuff on the test here. So let's close that up, keep on moving right along. Only a couple categories left. Conduit bending. There's not a ton on this, but I think it's worth reviewing. These tables are taken right from your textbook. Keep in mind here a couple things we want to know about. First of all, they're going to ask you about some shrinkage on an offset. Let's look at the multiplier first. So for any offset, right, which is 2 bends. If I'm doing for instance, a 30-degree offset, my multiplier, or my distance between my marks, is going to be this value. So for 30, it's going to be 2. If I'm doing 45-degree bends, it's going to be 1.4. But then my shrink per inch of offset depth. So for every inch of offset using 30-degree bends, I'm going to lose a 1/4 inch. Okay, so some nice values to keep in mind. I'm telling you, they will come up. This, I think, is kind of an abbreviated version. I think this table is far more helpful than this one, to be honest with you. But then we have this one for your saddles as well, which I don't think actually comes up on the test. All your honestly, all your conduit bending stuff, I think you can glean from this table right here. So keep that one close at hand, or keep that in mind. And then finally, to sort of finish this thing out, your unbalanced loads. There's just a couple questions, and what I mean by that is, it's another way to say, okay, we have our neutral conductor. If I have circuit 1 has 6 amps, and circuit 2, or let's use circuit 3, has 5 amps on it, and they share a neutral, what is the load on my neutral? Well, it's the difference between the two. 6 amps on A phase, 5 amps on B phase, the difference is obviously 1, so my neutral would carry 1 amp. The reason we can say that because number 1 is on A phase, circuit number 3 is on B phase, right? So the way we count these, if you don't already know, 1, 2, 3, 4, 5, 6. If you were to follow out this bus bar, here's your A phase comes in on this little lug right here, B phase comes in here. You can kind of see how this kind of has this like almost zigzag or finger pattern here. So if you can imagine, this left bus bar is connected to A phase. So here we have a connection, and then we skip a row. Then we have a connection, and we skip a row. Connection, skip, connection. So we have A phase, B phase, A phase, B phase, A phase, B phase. Same exact thing on the other side. So that's how you can tell which breaker is attached to what. That's the point I want to get across to you guys here is circuits 1 and 2 are on A phase. Because if we use this row as our reference, breaker number 1 would sit here and connect to this little piece. Breaker number 2 would sit on the other side and still connect to that little piece. So they're on A phase for both cases. So we have A phase, B, C, C. We would continue. Well, this is being a single phase, we'd actually be A, B. Then we'd start over. A, B. I'm used to a 3-phase panel where it goes A, B, C, but with a single phase, we're going to go A, B, A, B, A, so on and so forth. So that's how we tell which phase those circuits are on. So if we share a neutral amongst opposite phases, the neutral current will subtract. So if I have 10 amps on A phase, 10 amps on circuit 1, 12 amps on circuit 3, 1 is A phase, 3 is B phase. I have 12 on A, 10 on B, 12 minus 10 is 2. I have 2 amps on my neutral. However, if they're on the same phase and they share a neutral, which we can't do, but if I had 10 amps on A, 12 amps on, 10 amps on 1, 12 amps on 2, since they're both A phase, they add up, so I now have 22 amps on that neutral. So that's really all you need to know about the unbalanced loads there. But anyway, that's obviously not everything you're going to see, but I thought it was the biggest ideas, the most we want to cover in about an hour here. So take your time. Take the time to watch these videos if you haven't already. Again, it's intended to be a 4-hour test, so don't rush it. 80 questions. Take your time. I wish you guys luck, and hopefully we will be seeing you all out there next year in year 2.